All right, let's see what we got. Study is done on the population of a certain fish species in a lake. Suppose the population, P of t, after t years, is given by this function. Okay, so the initial population, well, this is an exponential function. Okay, we know that, partly because they said so, but also mainly because the independent variable is in the exponent. All right, so when that's the case, the number out in front that's not being raised to a power, that's always your initial population. Okay, and it doesn't say it's measured in millions or thousands or anything. So yeah, just 510 fish, because hey, who doesn't like fish? All right. So does the population represent growth or decay? Well, when the base of the exponent in an exponential function is greater than 1, it is growth. Now, if you are not sure about that, I mean, you could always just, where's the button? Okay, 510, 1.36. You could always just go here. Whoops. Okay, just plug in the function and then go to the graph and say, all right, what have we got? Oh yeah, its initial population is 510. So the y-intercept is 510. This only goes up to 10. So I'll just go zoom 0 and go capture that. And look at that. From right to left, it's going up. So yeah, it's definitely increasing. If you want to double check the answer to part A, you could go to the table and say, all right, what's going on at 0 days or 0 years? At the beginning, 510 fish. All right. So by what percent does the population size change each year? Well, remember the base of the exponent, that tells you how fast things are growing. That means that every year you end up with 136% of what you started with. In other words, the 100% that you already had plus another 36%. So you increase by 36%. That would be your answer. Okay, on this one, there was a sample of 200 milligrams of radioactive substance to start a study. Oh, fun. Since then, the sample has decayed by 2.8% each year. Let t be the number of years since the start of the study. Y is the mass of the sample in milligrams. Write an exponential function relating y and t. So all we do is create the function. All right, so yeah, it does say exponential there, but it's not going to say that on the test. I see radioactive, and immediately I know exponential decay. Even if they didn't say decay, I would still know exponential decay because that's just how radioactive substances work. All right, so the question is, what's our A and what's our B? A is what we start with, 200 milligrams. And B is what percent we end up with. So the sample decays by 2.8% every year. So every year you start with 100% of whatever, and you lose 2.8%, which means you end up with 97.2%. So 0.972 is the percent that we end up with. That is how you do these. It's a good thing to practice these before you move on, because after this, they say, okay, go build the function and then use it. So you don't want to be, working on building the function and figuring out how to use it at the same time. Okay, so we're going into Microsoft Word here, just because this got really small when I zoomed out. So I can do a little better here. All right, so we are told that we have the exact same collection of points on all three of these. Okay, the question is, which curve best fits the data? Which black curve best goes through the pattern of the data? I think we can all agree it's that one. All right. So use the equation of the best fitting curve from part A. So this little piggy right here. To predict the area, because that's the whole point of this stuff is, make predictions. Predict the area that the forest covers after it is inhabited for 13 years, and round your answer to the nearest hundredth. Okay, so let's jump back to the actual Alex thing. All right, and oh, it never did give the context. Oh well, whatever. Okay, points. Okay, so we know that this is figure 3 is our guy. So we're going to plug that in, and what do we got? 0.92 raised to x. Okay, so we've got the function. They gave us the function. That was pretty slick. All right. They don't tell us which, if the x-axis is the area of the forest, presumably measured in square miles, I guess. I mean, it might be acres, but I doubt it. That's pretty small for a forest. Or if it's time. So we've got two variables, square miles of forest versus time. I'm willing to bet that the y-axis is square miles of forest, because only going up to 20 square miles of forest is not a lot to work with. So this is probably time right here, like 20 years, 15 years, and so on. I apologize, they did not include that information. Okay, so use the equation, the best fitting to predict the area that the forest covers, so predict the y value when x is 13. All right, well, our line that we're using to estimate the data is pretty close to it. It's quite close. So 13, let me turn this back on. 13 is going to be about there for our x, and that's going to correspond to right there. I don't know, what is that, about maybe 800? Okay, 800, 850. I don't know. Let's find out. We'll get a better idea from the calculator. So let's go down to year number 13. I guess we could just plug it in. All right, 837 and a half year or square miles. So after 13 years, we estimate there will be 837 and a half square miles of forest remaining. Okay, and that the forest is diminishing in size for erosion, deforestation, nuclear blast, bugs that get into the trees, destroy the trees, and then once the trees are gone, the other things tend to go. All right, so whatever. But now, one thing to think about is this prediction we're making is 13 years into the future. Okay, the further you go into the future, the less accurate your model is likely to be. Usually what happens is you say, all right, well, we found this to be true, and this and this, and we get all these cool points here. Okay, and then you say, all right, well, we get this cool trend line here in black, and in the future it'll look about like that. And then you say, all right, what might happen over here in the future, over here, and the further you go into the future, the less accurate your model is likely to be. Okay, if you use this model for 50 years into the future, it's not likely to be accurate at all. Okay, it might be, but it's not likely. Okay, just because it's just so far into the future, it's difficult to predict. All right, so here we go with more word problems, which are the only really fun ones in exponential. So the number of milligrams, d of h, so d for number of milligrams, and it's dependent on h, which is number of hours that the drug has been in the bloodstream after injected, is determined by this function. Now, once again, we've got the e here, so we're not using this pattern for exponential function. Instead, we're doing cert, okay, where e is about 2.7, so that does not vary. It's not a variable, and we have an e button on our calculator. Okay, c is like a, that's the initial amount, that's why it's out front. T is still time, and then R is just that exponential rate, determining how fast things are growing. Okay, so when the number of milligrams reaches 7, so we start off with 35 milligrams in the bloodstream, and the bloodstream or the muscles and everything are absorbing it. So so it's going down, down, down. It's a decreasing function. I mean, if you said, no, it's increasing, then that means you get an injection, and then the amount of drug in your body just keeps getting bigger and bigger. You'd be like, that's weird. Okay, so when the amount gets down to 7, well, it doesn't say 7 hours. It's 7 milligrams. So this 7 is the amount you end up with. Then at that point, the drug is to be injected again. So how much time is needed between injections? Or in other words, how long does it take to go from 35 milligrams down to 7? Okay, well, one thing we could do, and maybe this is like cheating, but I can live with it, is type in the function. There it is. What was it? Negative 0.35, negative because it's decreasing, it's decaying the amount. We could just go to the table and say, all right, at hour number 0, 35 milligrams. When did we get down to 7? We get down to 7 milligrams somewhere in here. So at about 4.5 hours. Okay, boom. I mean, that's not perfect. I mean, we could say, all right, well, let's start at hour number 4 and go up 1/10 of an hour at a time. And then, when do we get to 7? We get to 7 at about 4.6 hours. Okay, so so basically about every 4.5 hours, give them another injection. Now, that is probably not the way that the author wanted me to do it, but that's okay. So plug in 7 for D of H. You got 35, yeah, okay. And then divide both sides by 35. So you get 7/35. That's going to be 1/5 when you cancel the 7s. And now I have an exponential function. Now it really is an exponential form, ready to be converted to log form. And we divide both sides by negative 3.5. And I get ln of 1/5 over negative 0.35 is h. And now it's party time. I get to go, and I already know my answer should be about 4.6, maybe 4.58. I don't know. All right, so we'll go ln of 1/5. Okay, and then divided by negative 0.35. And yeah, okay, so 4.598, did it say how to round it off? Nearest 10th. Okay, so to the nearest 10th, yeah, 4.6. Just as we, expected from the table. Another way to do it would be to say, take this initial equation right here with the 7 in it and say, hey, it's an equation. Let's graph the left and graph the right, see where they intersect. Okay, so if I do that, there's the right, there's the left, and let's go to window. Okay, we don't need to go to hour number negative 10 hours before the injection. Let's start at hour 0, and let's go up to hour, well, we already know the answer is between 0 and 6, so that's good. All right, and he starts off at 35 milligrams and then goes down. So I don't know, let's go down to 0. 7 should be enough, but he won't go below 0 milligrams of the medicine. And so there's that. So here is, so the blue one maps out, charts out, how much is in him. And we're saying, when does he get down to the 7 milligram mark in red? So second trace 5, enter, enter, enter. And that's getting hard to read, sorry. Okay, and we get that. Hey, that number looks kind of familiar. If I go back to the main screen and I type X, because that number is temporarily stored there, I get the exact same thing. Okay, so I've solved it multiple ways. I can double check my work and make sure that I'm doing it right. You should too. Okay, so now once again we've got oh whoops, it's not turned on. A CERT equation, and the amount of money invested in a certain account increases according to the following function, where y naught, y sub 0, is the initial amount of the investment. Okay, anytime you see a sub 0 attached to a variable, that means the initial amount, the beginning amount. So when you see v sub 0, that's the beginning velocity. When you see r sub 0, that's the beginning rate, or whatever r stands for. And y sub 0 in this case stands for the initial amount of money. And y, that's just, the final amount, or whatever you end up with. T is years, like normal. So after how many years will the initial investment be doubled? Okay, so it doesn't tell you how much you start with. So you can pick whatever you want. You can say, well, I'm going to start with $1 million. Okay, blah, blah, blah. Okay, but you don't have to. You're getting the same answer either way. You could just say, I'm going to start with y sub 0, and that's fine. So if that amount doubles, then it becomes 2 times y sub 0. There, our money is doubled from whatever it was. Now at this point, I divide both sides by y sub 0, and I get 2 equals e to the 0.025 t. Now notice, I got a 2 on the left side. It didn't matter, like I said, it didn't matter what my starting amount was. That's the nature of exponential growth and decay. It doesn't matter how much you start with. How long does it take for it to double? Well, if you have $1 in there, it'll take the same amount of time for you to double that to $2 as it will to get from $1 million to $2 million. Okay, that's why when you're hanging out with somebody and they're getting ready to retire, and they're like, yeah, I'm going to hang in there another couple of years. And you're like, why? And you say, I'm going to keep working there. Well, I want to have more money to retire on. Well, first of all, that's 2 more years that their retirement account doesn't need to provide for them. But more importantly, at that point, their money is no longer right there. It's like right here. And so 2 more years, your money, the graph is very steep, and they might pick up another 100 grand during those 2 years or more. It kind of depends on a few things, particularly how much money is currently there. Okay. All right, so we can now convert to log form. Okay, and then divide both sides by negative 0.025. And we go to our calculator. Yeehaw. So ln of 2, okay, divided by negative 0.025, so 2.5%. All right, and negative 27. That does not make sense. I have done something wrong. Let's see if I can figure it out. Oh, duh. Jeez, I'm sure you guys noticed. Why do I have a negative sign right there? I don't know. So I got to get rid of the negative. That's what's causing the problem. Yeah. Okay. Yeah, that would not make sense, because then if I have a negative r value in a CERT equation, then that means it's decay and the amount is going down. So I didn't think about that. But see that? Mistakes happen to everybody. So let's go back here. Delete. Where's my delete? Right there. Okay, and we get 27.7 years, and yeah, that's how long it takes. How fun. Okay, last one. A certain substance decomposes according to a continuous, boom, right there. I'm thinking y equals CERT. Continuous exponential decay model. To begin an experiment, the initial amount of the substance, I'm talking about C, is 9,900 kilograms. How heavy is a kilogram in Earth's gravitational field? Well, it's about 2.2 pounds, a little over 2 pounds. Okay. All right, so after 7 hours, there's 3,861 kilograms of the stuff left. Sweet. Okay, So let t be time. What a surprise. Since the beginning of the experiment. And y is the amount left over. Write a formula for all this stuff. Okay, so we got to fill in the two boxes. Cool. Well, we know that, whoops. Okay, let me write a little smaller. Okay, so we know that C is 9,900 because that's the initial amount. And so we got that. Cool. 9,900 e to the something t. All right, so what's R? Well, we know that we end up with 3861 after 7 hours. Okay. So we've got an equation with just a single variable, because remember, e is not a variable. It doesn't vary or change. And now we just go solve for R. So let's divide both sides by 9,900. Then we can convert to log form. Let's see, 3861, 9,900. And then divide both sides by 7. And I need to do a little erasing now because I'm going to work on the calculator. All right, so then, all right, so we'll go ln of 3861 divided by 900, and then all of that over 7. Again, the answer should be reasonable. I get negative 0.13, and the substance started at 9,900, and it's going to go down to 3861. So yeah, it's going down, and when it's going down in the CERT equation, R is negative, so this makes sense. So negative 0.13, 0.13 is cool, I guess. Negative 0.13 t. All right, cool. So we got that. And now we're ready to keep rolling. Okay, so how much of the substance is left 19 hours after the beginning of the experiment? Okay, I'm going to get a little cute here on this one, on the calculator, because I want to type in the function. Okay, and then second ln. Okay, and then I need the this number here. Okay, so here's a little something new for you. Maybe I'm just going to take that, and because I don't want to round it off. I want to get really accurate data, so I'm going to store that as a. You don't have to do this, but whatever. There. Anytime I hit the a, it's this whole number, not just the 0.13, but all of it. So I'm going to go a. You can just do the negative 0.13, but I do want to show you what you can do. All right, and then the x. All right, so then what was the question? I don't even remember now. Oh, in 19 hours. All right, so when t is 19, so I'm going to go to my graph. Whoops, or table, I mean. All right, let's make this a 1. And you know what? Might as well just jump to 19 while I'm there. All right, so at 19 hours, we are down to 768.54. Okay. I wonder how different that would have been. Probably not that much if we didn't round it off. Okay. Let's take a look here. So negative 0.1, or if we had rounded it off, sorry. So if we had rounded it off, we would have the y2. All right. And at 19 hours, it makes a bit of a difference. Okay, that's different by, what is that, about 70. Different by 70 kilograms. Now, in this situation, I don't know, the nature of the experiment, so that might not be a big deal. It might be. And the further out you go, well, yeah. So anyway, whoops. You can just kind of explore it around. So it looks like, yeah, at 15 hours, it was an even bigger gap, about 80 90 or whatever. Anyway, so that's kind of how it's done. And but yeah, at 19 hours, I'm going to go with the more accurate one and say 768.54 kilograms. That is it.